All right, so today I want to talk about an interesting application of integration. Okay, volumes of revolution. We're going to be doing volumes of revolution pretty much, I think, until about darn near the end of the year, or at least into next week. Um, and we might do one more thing before the end of the school year next Friday. Okay, so let's think about this for a moment. Let's think about if I were to say take a line segment, okay, and I'm going to say this is at 4, okay, a height of 4. So we're talking about the line y equals 4, but I'm only really interested in it between 2 and 5. Okay, so obviously, I mean, I could do some calculus right here if I really wanted to, or I can just use some basic geometry and find the area underneath that line segment. Okay, so it's just a rectangle, height of 4, width of 3, so got an area of 12. Okay, nothing exciting. But if what I do is I say to myself, what would happen if I were to take this line segment and revolve it around the x-axis so that it now does, well, what shape would it be if I did that? If I took that line segment and rotated it, what would I have? What shape would I have?
Circle?
Well, if I looked at it this way, it would certainly be a circle, but it's a three-dimensional object. So what three-dimensional object does that make? It looks like a circle from this side. What shape is that? Three-dimensional
Cylinder?
object.
Cylinder.
Yeah, it's a cylinder or a disc. Okay. And that cylinder has a formula for its volume. And the volume of a cylinder is the area of the circle times the height. So that would be pi r squared h is the volume. Okay. And that's fine and wonderful because, you know, this is a very simple shape. So if for this particular one that I've drawn, what is my r?
4.
4. How did you get it? How do you know?
Height of the rectangle.
Yeah, it's the distance between the center and a point on the edge, which is the definition of a radius, right? And the height would be this, right? And then in that case, it's just the thickness of the disk, and that would be 3. Okay, cool. Well, now let's take this idea and apply it to something a little bit more interesting than just a line segment. Okay. Let's take, for example, a parabola y equals negative x squared plus 4. Okay, so I'm at 4, I'm at 2. Okay. Now, this is the beauty of that whole Riemann sum stuff that we did. Okay. So let's find the area, you know, let's look at this thing as it would be if it was a Riemann sum. So we'll just make life easy and we'll just do one partition here at 1, and we'll do left-handed Riemann sums. And so at 1, the height is at 3. All right. So I've got these two blocks, these two rectangles that come from a left-handed Riemann sum. Okay. Now what I'm going to do is I'm going to take these and I'm going to spin them around the axis. Okay. And so when that happens, you wind up with this shape that kind of looks like a layer cake in a way. You know, this kind of two discs on top of each other, like a ugly looking wedding cake or something like that, you know? And now we've got two discs that we care about. And we get a volume. Now we would have, you know, the volume of this guy would be, you know, pi, and the radius of this would be that radius, right? And so that radius was 3, and its height was 1, and this guy's radius is 4, and its height is 1. And so we can find the volume of this cake by using two Riemann sums. So what we can continue to do, like we did with Riemann sums, is use smaller and smaller and smaller subdivisions until finally we get something that looks sort of like that. And on the other side, so what I've done is I've actually made that shape, and I'm going to share my screen so you can see it. Hold on. Let me find it. Nope, that's not the one. All right, can you see? Are we all looking at a GeoGebra file? No, not yet. Okay, good. Are you now looking at a GeoGebra file?
Yeah.
Okay. So what I've got here is I've got my my curve from the parabola. Okay. And what I'm going to do is I'm going to spin this thing around. Let me see if I can get it. So there it is in 3D. I'm going to spin this thing around the x-axis. Actually, I'll do it this way. And as you can see, it makes this kind of dome-looking shape. All right. And so to find the volume of this shape when it is complete, in that, you know, we're not making it with series of approximations of layer cakes, what we have to do is we have to consider making these partitions smaller and smaller and smaller. Okay. So what we wind up having is, if we look at that equation, my radius at any given point, the radius is given by the function's height at that point. So we wind up with pi r squared, and then the height was the change in x, the small little interval. Well, we're adding up all of them, right? But if we go ahead and say, you know what, I want to make these guys smaller and smaller and smaller and smaller and smaller, that's taking the limit as n approaches infinity. And so we wind up with the integral. I can pull the pi out, it's a constant, of the radius squared, and my delta x gets infinitely smaller until it's just dx. And we're going to go from A to B. And so this is the volume of revolution of a function about the x-axis. This is also known as what is called the disk method. Because what we have is we have a boatload of disks, little disks that get smaller and smaller and smaller. Okay, so let's try a problem or two. All right. So let's take, has everyone got this copy? We're all good? Okay, cool. All right. So we're going to go and look at y equals the square root of 9 minus x squared in the first quadrant. And we're going to revolve about the x-axis. Okay. So the first thing we have to figure out is what are our bounds. So we take a look, I mean, you can look at the graph, or you just set this thing equal to 0. And because we want it to be in the first quadrant. Does anybody know what shape this is, by the way? It's got a name. This is a circle. Yeah, this is a circle of radius 3. All right. Okay. So go ahead, see about setting up the integral. Don't forget the pi. Everyone forgets the pi. Okay. And revolve this guy around the x-axis.
What would your A and B be?
I'm sorry. A would be 0 to 3. Yeah,
Oh.
A is 0 and B is 3. And of course, the square and the square root go away. Who got it? Now, let's confirm our results just because we can, because this is a shape that we already know. So if I were to take this arc, this quadrant of a circle, and spin it around the x-axis, what shape would I have?
Half of a sphere.
What's that called?
Semi-sphere.
Hemisphere. Now, the volume of a sphere, I'm not even going to ask if anybody knows it because nobody ever does. 4/3 pi r cubed, but we're only dealing with half of it, so it's 2/3 pi r cubed. And if we plug in r as 3, we wind up with 2/3 times 27 pi, which is 2 times 9 pi, which is 18 pi. So that is the correct answer. Okay. Now, let's do one. Do another one. Okay. Get another one here. All right. Ooh, that'll be fun. Okay. Do that later. All right. How about something simple? In the first quadrant. That's all I'm going to give you. You guys can figure out the rest. Finding the bounds is important, so know how to do that. Okay, so yeah, if I were to take the square root, sorry, I lost my recording there for a minute there, but once I solve for x, once I solve for x, and I take that square root, you would get a plus and a minus, but we're only interested in this part, so I'm just going to take the plus part. Okay. Now, again, it's pi, and my function squared. Dy, because I'm going to go from here up to there. So my bounds are now 0 to 4. And just to show you what that would look like, well, let me ask you this question. Do you think it's going to have the same volume or a different volume from when we spun it around the x-axis? Anyone want to take a guess? You got 50-50, same or different?
Same.
Okay. Now let's think about what this thing is going to look like. There we go. So I'm just going to put this guy back. So now when I revolve around the y-axis, it takes on a different looking shape. More like the tip of an airplane or the tip of a rocket or bullet or something like that. So kind of cool looking. All right, so let's go ahead and find this value.
Mr. Ronco, it says 4 minus y squared, isn't it just 4 minus y?
Where?
Right there. Because before it's a
Oh
square.
yeah, why did I?
before.
Oh, because I misread it. There's no square there. So good catch. Thank you. So that is now just. I was like, wait a minute, I was having a problem with that one. So these are different volumes. And generally that will be the case. So like, let's take a weird looking example just to kind of like really illustrate how they would be different. Let's take something like that shape. Now, if I were to spin that around the x-axis, what would it look like? Well, let's try one. We've got a few minutes. All right, so let's take the function. Let's do, where's that? Let's do x plus 2. So that will be my function. And this guy is a parabola. I'm gonna put a negative sign on it. All right. Now, if we think about this for a minute, we spin this guy around the axis, okay? What is he gonna look like? He's gonna look something like that, right? But if I spin him this way, what would it look like? spin him around this way. Well, I actually have that one too. So, but this one we're not ready to do this integral yet. We're gonna learn this part tomorrow. Because we haven't dealt with, this is the same basic idea, it's an upside down parabola. But this guy, we haven't dealt with like the, empty spaces. But if we were to spin this guy around the x-axis, we get this strange looking solenoid like shape. But if we were to spin it around the x-axis, sorry, the y-axis, what does that look like?
Pound cake.
Yeah, a bundt cake. Yeah, that's the name of that kind of a shape. Right. So they would have drastically different volumes depending upon how far away this was from the axis, but it would still have the same volume going around the x-axis if I move this thing out to the right. So I'm going to give you guys just a couple of problems to do, not too much, because we're going to learn a little bit more and do some more exciting things with this next class. But I just kind of wanted to open up the door to it today. Okay, so everyone have a good afternoon, and I will see you all tomorrow. Bye-bye.